Hello, everyone. We have now confirmed that they can hear us online. We have 75 more people there, and I'm guessing we're approximately 20 in the room. So I'm glad this event has attracted so much attention, and to me it feels a little bit like a kickoff on the work that me and all of us here want to do at SAFER this semester. So we are at SAFER. We should say that this is an event, a presentation, I would say, a lecture, and this is organized under the Systems for Accident Prevention and Automated Drive research area, and more focused in the competence network, what we call ourselves, safety assurance. So how to argue that automated vehicles are safe. And I was fortunate enough in the Ivy conference in Aachen to run into Hans-Peter Schöner, Dr. Hans-Peter Schöner, I should say, who has a long career, a lot of it at Daimler, where you have been responsible for testing and ADAS, and you've been leading those activities. So I know you've been in Sweden many times before. I think both Arjeplog and here in Gothenburg.
Yes, and in KTH for my PhD, I worked a lot of time together with a professor at KTH in Stockholm.
And now we've been to vacation here for 2 weeks as well.
And that's one of my favorite locations, Sweden. Yes.
So we're very happy to have you here, and I'm glad that you stopped by in Gothenburg on your way back. So without further introduction, I would like to leave the word to you. And if you need anything during the presentation, let me know, and I will fix if it's sound or something else.
Thank you, Frederick. I'm glad that I can be here, and I'm convinced that Gothenburg is a very important location for vehicle safety, and especially this institute. So I'm very happy that I may give a presentation here on some of the experiences which I've made. Of course, during my time at Daimler, I was at Daimler almost 30 years, 15 years responsible for testing on the proving ground, in driving simulators, and also especially for autonomous driving at the end. And I started a project together with other German companies, the project Pegasus, which should define how to test and what to test, what are really the goals for the safety level of autonomous vehicles. That was many years ago. At the same time, I was responsible safety engineer for testing. So all the people who went to the proving ground, who used autonomous vehicles with function which were not completely certified and tested to make sure there are no dangers. And not only for testing, but also for everyday work life at the company, building up vehicles, working on machines, and so on. So I looked at safety not only from the traditional vehicle perspective, but also from the everyday safety issues which you have working among other human beings. So a very human-centered looking at safety, not only vehicle-centered looking. And I tried to put some of these experiences into my slides, which most of them were created in a cooperation with JARI and JAMA. That's a Japanese organization. JARI is the research organization for automotive research in Japan. And they supported my work to write down my ideas. So the ideas which I present are my ideas mainly. Of course, they are somehow modified by the discussions with the Japanese people. They supported it and they made it possible. And I should greet from Dr. Jacopo Antona Makoshi, who got his PhD here at Chalmers. So he is very glad that this work is also presented here in Gothenburg. Let me start with, let's call it state of the art of autonomous vehicles. Mercedes just published this first autonomous vehicle. The video is in German, so I just speak in English over it. That's the first level 3 autonomous vehicle. And of course, it has a lot of functions, traditional functions, which are the same as in traditional vehicles. And they are using it and he is explaining how to use the normal ACC systems, and he's still telling him, now you are still responsible for driving. That's one of the important things. So if you start the level 3 autonomous driving function, then the vehicle is responsible for the driving tasks. The driver can do something else. He can put his mind on other things. He still has to be there, but that is the most important point. The responsibility for the driving tasks goes to the vehicle. So I asked myself, what does that really mean? What is responsibility and responsibility for the driving task? These ideas which I present were started by a judge which gave a presentation to the people who were responsible for safety at Daimler and telling what really means responsibility. And he said a judge looks at responsibility afterwards, after something has happened, an accident or something like that, and he would ask questions. So being able to respond to those questions is the essence of responsibility. And questions would be like this: can you explain how this accident could happen at all? So do you have an idea on what was really going on? Why didn't you see this accident come up in a much earlier stage? And how did you act, and why didn't you react fast and strongly enough to avoid the accident? You see, here are some questions: how and why. The witnesses are not asked why, but the responsible person is asked why. And how did you act? You were responsible, you had to avoid something. Let's summarize. First, have a clear understanding, and you can express that with quantitative measures of the risks of driving. Second, you have to apply continuous, complete, and vigilant monitoring of the scenarios with respect to dangers. And third, you have to know your available actions to reduce danger, including a sense of your own limitations. All these three things are very important parts of responsibility, and that not only applies to accidents, it applies also for being responsible for business. Of course, it's not the safety, it's the success of the business, which is the main purpose. But if you want to be firm in front of a judge where you have to show that you acted responsibly, you have to implement these principles when you develop a vehicle. So you have to have this in your mind when you do the preparational work. Now, the title of my talk is about tactical safety. That word needs some explanation. Tactical behavior of humans, what is this? Tactical comes from military vocabulary, and there it means put yourself in a position where you can't be attacked or you can't be defeated easily. And for human drivers, it's they look ahead, anticipate possible risks, in addition to recognizing acute prevailing danger, and they reduce speed, longitudinal distance to other vehicles, and also lateral position to other vehicles, and maybe in the lane, the distance from whatever, a hole in the lane. And they do that on faint cues, changing behavior to the safe side because they have, now quite often you would say they have some sixth, or in German we call it seventh sense, I don't know how you do in Sweden, about what might happen. You have seen so many different situations which develop in a certain way, and then you have a sense like, oh, the car in front is going so slowly, it's something unusual. Maybe this guy is looking for a parking spot and then he suddenly will brake when there is one. So be prepared for that. Understanding the performance limits in unusual situations, like there will be an emergency braking, and you have to know how fast and how strong you can brake. And you have to know the conditions when such unusual conditions are likely to occur. And another part is showing cooperative and fair behavior. Some people say that's not safety. I believe strongly it is safety. If you don't let somebody else in, he will be bolder and bolder to get in, and at some point it will be dangerous. So cooperative driving is also a matter of tactical safety. And also, there are rules in traffic, but we all know, in German we have the saying, there's no rule without exception. I know there's something similar to that in Swedish. And that's the point. You have to understand what is the meaning of the rules. You have to understand when you come to the limits of the applicability of the rules, and then it's responsibility to decide what to do. I come to an example later. So here's my tactical safety definition. Change your behavior early and smoothly, not abruptly, based on indicators for possibly dangerous situations in order to avoid potentially uncontrollable situations. This term was not invented by me, but there's a CertiCAF project in the United Kingdom, and these people coined this word, and I think it's a very good term to describe what I really want to say. Key message is safety in traffic does not only depend on being able to react to given critical situations, and that's what most test scenarios do. They put a vehicle in a critical situation and try to find out whether they can react in the last second. No, that's also important, but also it is important to change the behavior in order to prevent critical situations. This is also reflected in the formulas which have been used for many, many years as the risk contribution of a single contributing scenario depends on three factors. One is the possible severity of an accident which can come out of this. One is the controllability or the uncontrollability is 1 minus C is the uncontrollability of a situation. And E is the exposure. So how often do you get in those situations, or how likely is it to get into those situations? Let's look at that a little more with respect to driving situations. The severity is addressed by passive safety, which have been for many years in our cars. Active safety is detect dangers early and react fast and appropriately. But the E, how often do you get in such situations? For the level 2 ADAS systems, it has been the responsibility of the driver. But that is a new option for autonomous driving. Look ahead, drive predictively, so others will be able to anticipate what you are doing, but also you know your own limits. And I propose, together with the CertiCAF, to call this tactical safety as a third part, together with active and passive safety. There's also a legal aspect of that. The German traffic code is translated here, but there are very similar sentences in other codes of other countries, in England, in America, in Japan even, and regulations which say anyone who participates in traffic must behave in such a way that no one else is harmed. Of course, that's collision avoidance. But there is more. There is no one else should endanger anybody else. And that's careful and predictable driving. Avoid dangerous situations. And there is also, but with a lesser priority, it says, if more than under the circumstances unavoidably hindered or bothered. So that's the cooperative driving part. It says you have to expect that you will hinder some people in some situations. It's unavoidable, but you should keep this down, and the cooperative driving is part of this general regulation. Now let's talk about risk, danger, and behavior a little more in detail. And I want to start with one popular thing, that's those ethical decisions in hypothetical dilemma situations. I think it was a professor from California who brought up the situations. There is a trolley like in San Francisco going downhill, and the brake will not work. But you're able to switch. And what decision would you take to kill this person or the other persons? Somebody else, I think this was Geislinger, then put it a little different like that. You cannot brake, kill those people or drive this way and you will kill only one. What is better? I believe asking such questions is even unethical. The UNECE and also the EU regulation have made some general statements about that. Automated vehicles shall not cause any non-tolerable risk, meaning that under their operational domain, they shall not cause any traffic accidents resulting in injury or death that are reasonably foreseeable and preventable. So, are those reasonably foreseeable or not? I would say this with the brake is foreseeable. But that's the reason why all cars, since many, many years, have been designed with 2 independent braking systems. So this situation, just the brake fails, is not the state of the art of vehicle engineering. We have implemented solutions to avoid coming into this dilemma situation. And that's the way to go. There are some people, they say, oh, I'm not responsible for any course. But if it's foreseeable that that course will be there, that somebody else will bring you in a situation, I think if you go to a judge after the accident, they will ask you, didn't you see that come? Wasn't that foreseeable? And that is an important and difficult question, of course. So let's see. Foreseeable, I believe it's even rare cases, including incidents caused by others. Things like predictable misuse. You drive in a Tesla like it would be a really fully autonomous vehicle. Acting against the rules of others. Okay, you cannot really say, oh, on a highway, nobody should come in my direction, but it happens every day. So you should be somehow prepared for that situation. Reasonably, how likely, with what quantitative arguments from accident statistics, severe accidents should be considered differently than bagatelle. So it's a question of how often and how severe the accidents will be if it's reasonable to put this into your list of situations which you have to cover safely. And preventable, there has been a big discussion, especially with the Japanese people. Maybe they had some problems in translating preventable into their language. And they were always focusing in the beginning on the first sentence, control an already dangerous situation by control actions. So that's really the C of my risk formula. But also preventable means, like with building in 2 brake systems into a trolley, avoid risks in order to prevent to get into those situations. I believe hazard and risk analysis are the good way to go through those points, but you always have to check all the 3 points to assess the exposure, the controllability, and the severity of operational dangers and maybe also failures of components. And you have to implement methods of not controlling, avoiding dangerous situations. And dilemmas, like we have seen before, can contribute to this analysis. So you need to make your brainstorm to find all those dangerous situations. But you have to be able to say it's not only the matter of last second control actions which have to avoid that. There are also ways to prevent a risk by avoidance, by implementing technical solutions beforehand. And that's the goal of a dilemma, bring you to that thought. How can you get away from coming into such situations? There are 5 categories for reasons of risks and dangers, presented it the first time in 2014. Failure of component and hardware deficiencies. This is very well covered by the ISO 26262 standards. But then what is new with autonomous vehicles, because up to now it was a task of the driver, deficiencies in sensing road, traffic, and environmental conditions, like the glare, where are the lane markings there, deficiencies in control algorithms, when the situation gets too complex and too difficult situations. It could be something like that. Also, that is Turkey in some national park in the US. But just last week, I went to Salzburg, and there was an intersection which was so complex with a lot of intersecting lanes. And, can you really handle that? I took some time to handle this before I understood which lane is providing traffic in which direction. Okay, but that's the challenge. And behavior-dependent accidents. What is the adequate behavior when you come to such a situation? It also takes some time to understand that. And if you have deficiencies in these, there might be problems. And there is another one which was the main cause of accidents for aircraft when they started to have autopilots. That was the faulty driver and vehicle interaction because of mode confusion. The driver or the pilot thought the aircraft was in charge of the situation. The aircraft thought, oh, that's a mode where the pilot has taken over again. And such situations have to be avoided, and such situations have to be tested. Interesting is that those are design specific, and we have a long tradition at Mercedes, at Volvo, to do this. And these external conditions, they are really new for the autonomous vehicle. So I focus on those now. One example for a dilemma with respect to rules. The question is, should you leave your lane for a dead animal or drive you over it? In this situation, okay, nobody oncoming, a dashed line, okay, you pass. It's very simple for a human being. But for an autonomous vehicle, okay, this one would be easy. But what about this situation? It changes just by this white stripe. Now there is a rule. You should not cross a solid line. But in this case, every human driver would know his experience that just passing with a slow speed, and of course, watching out for oncoming traffic, it's not a problem. But it's because you understand the limitations of that rule of this white line. And there are many other rules like that. Responsibility includes decision beyond the specific rules. And it requires, you have to know the meaning of rules, and you have to understand the level of risk by bending a rule. In German, we say you can bend a rule, but a law, it's fixed. So we make a distinction between a law. You don't change that because of your own responsibility, but a rule is made for controlling or for helping to control standard situations. In certain situations, it's part of our lives to bend rules. Let's come back to this formula. Actually, it's not me who invented this formula. I want to point out this has been used in aircraft safety. When I started to work with this field, I looked very much in the Federal Aviation Association Handbook of Flight Safety. And all those formulas, they are used in there quite extensively. I tried to understand what does that mean for behavior. And I thought there are two important parameters. One is the relative speed, and the other one is the available reaction time, which are the main factors for looking at reducing risk. And if you take the severity increases with relative speed between your own vehicle and another vehicle or another object. And the available reaction time does not really change anything to severity if the relative speed is measured at the time of crash. The controllability is not so much dependent of relative speed, but you need a minimum time for controllability to react. And then your controllability is good for longer times, but if you have more relative speed, you need to take out the speed difference, the energy out of your situation. So these are it's worse for the severity with highest relative speeds. It's better for controllability with longer reaction times. And with rules and behavior, the third part, the safety distance controls your available reaction time. Of course, speed also is in there. If you have the safety distance measured in following time, then it's really related to reaction time. And the speed limits, they provide a limit for the maximum possible danger which can be there because of an accident with two vehicles. And maybe some other things as well. But if you put all those together, I try to put this into one picture. If you take severity and controllability, you see down here, this is fine. Here it's more dangerous, and there's some part which is uncontrollable, but not very severe. If you take the safety distance, this takes away part of a big of the severity part, and the other very important safety risk coming from relative speed is covered by the speed limit. So behavior, like these behavior things with safety distance and speed limit, which you also can control by yourself. The speed limit is only the limitation, but you could choose to have a lower speed and to have a higher distance. That will be, this makes it possible to change this reddish part and to avoid the risk from maybe bad weather, which will bring the controllability over here. Maybe the visibility is bad and you need longer reaction times. So this center part can be controlled by changing your behavior with respect to speed and with respect to safety distance, in order finally to keep it all green or prevent it. In another slide, you see like this: if you have controllable factors and independent parameters like weather, traffic, infrastructure, those might lead to, from normal driving to complex driving situations, critical situations, and the accidents and the severe accidents are at the top of this pyramid. And the main point is, if for some conditions, whether traffic or infrastructure, the risk, the situation gets more challenging, then you have to change your controllable factors to come back into the normal driving, into the safe zone, away from the dangers. And these are dangerous, but the accidents are only up there. Looking at highway scenarios as one important thing, I was personally very much unhappy about how people look at high-speed driving in highways. And so together with the Japanese people, I put together the challenges for highway scenarios as a focus. Similar things you can do for the city driving, but there are a lot more. But the severity is much higher on the highways. So the ODD is where do you drive, is some people say, oh, you can limit it. But actually, this slide will tell you, you cannot really limit it. There are always creative human agents which have ideas what to do. And traffic conditions, for this reason, will vary indefinitely. You cannot predict what will happen. The environment is unpredictable. We have normal weather, which we all expect, but we know that there are floods, there are snowstorms. No human driver would go out in this traffic, in these weather conditions. But if we talk about at least formally about a level 5 autonomous vehicle, it's stated it can go out under any conditions. That's, yeah. So you have to watch the weather and you have to watch those conditions. And a huge number of participants and a long-term operation. At Daimler, the first thing I learned was whatever fault or mishap might happen, if you can imagine it, you might be almost sure it will happen at one day. So you have to avoid that. So even when you focus on the relative easy highway applications, there are unusual cases which cannot be defined exactly. And you need to somehow make a provision for that kind of situations. If you want to make it work, you need a set of rules which is free of conflicts within the controllable ODD under usual conditions. You can define usual conditions. Under these conditions, I have it under control. But this needs a supervision that you stay in those usual conditions, and when there is an unusual condition, they must be recognized. And you have to understand what happens if you come out of these limits of your usual conditions in the ODD. And then if you come close to those limits of the ODD, you have to work on tactical safety actions to bring you back in the ODD, or at least to reduce the exposure to such situations. And this is the part where I believe there are no test cases internationally specified for verification and validation whether the ODD conditions are supervised, about the knowledge about controllability in those situations, and about the adequate tactical safety actions. Here is an overview of the kind of traffic situations which we made in Japan, and we had 4 categories. One, which were difficult traffic situations. They occur every day with low severity, but since they happen so often, it needs to be flawless behavior. Extraordinary traffic situations, maybe they occur once per week or once per month in the traffic environment, like in the Swedish highways or in the German highways. They lead to accidents normally, they have high severity, and what can you do to avoid it and have no injury for those very high severity situations? And there might be some situations which are really out of your responsibility, but what can you do to mitigate the outcome of this kind of situation? And then there's a different category, long-range sensing. I believe there are some implementation or some situations which need the implementation of communication, and I come back to that later. Here's an overview of those situations. The first thing, you know there is a blocked road, but if the car in front of you is not braking, you follow this truck in a close distance, maybe in 1.8 second distance, you will not be able to brake if this car crashes into the standing end of a traffic jam. And he has made the fault, but you're behind. And if you are more driving than 60 kilometers per hour, your risk of being killed in this accident is very high. Merging. This test on how do you merge in dense traffic. Around Gothenburg and Stockholm, you have dense traffic. But it's not compared to the dense traffic we have in Germany every day. And so this kind of situation, merging in here, you cannot merge into a full street without violating the safety distance rules. So you have to accept that there must be done something temporarily. How do you do this? And it could also be you are not in this side where you have to merge in, but you are here on a continuous track and the others have to merge in. So that's cooperative merging. Test cases for these things are missing. And emergency vehicles, okay, you have probably the same thing. In Germany, this happens every day where you need some gap for an emergency vehicle to pass. And do vehicles really perform like that? The second category, know your limits in extraordinary situations. As I said, if you follow an unattentive driver, you can make a chart and you can find out that there is an unsafe region, a safe region. And between here, I can go into detail a little later on that. It's depending on your knowledge, whether there is flowing traffic or not, whether it's safe or unsafe. This cut-out example, this vehicle cuts out and there is a standing object. Can you avoid that? That's very similar to that one. Yeah, and also in the Pegasus project, a second one, you are the vehicle under test and somebody cuts in and then brakes. That is also a situation where it's maybe not your fault, but still responsible to avoid the accident. And there are some limits in the regulations. Oh, that you have to avoid. But what do you do beyond that? And now the rare but surely dangerous failures. The bridge is out. It's obviously not the responsibility of the driver to keep the bridge working. But what happens? Somebody warns other people. But let's start with the other one, which is more frequent even. You're going here and maybe you moved out that and there's an oncoming vehicle on the track where it doesn't belong. How do you handle such situations? No test case for that. It's all assuming this does not happen in the regulations. This kind of situation is normally a lot covered by just a human getting out and waving his hand. We as a human understand, oh, that's a sign, drive carefully and slow down. Can an autonomous vehicle understand such situations? Of course, there are some electronic features which can be implemented, but they have to be implemented. Bad weather conditions. I have been in my life in 3-4 situations where I just couldn't continue driving because of bad weather. And that's about the mileage which is covered in the whole community in one day or even in a shorter time. So it will happen. And it's predictable that it will happen that you cannot see. And there's no set of sensors which are fail-proof. And it's a common cause of all your environmental sensors, what you do in this situation. And then if the driver doesn't take over, although you have a level 3 request in 10 seconds, you have to take over. Yeah, and maybe if he takes over, is he able to drive to make safe reactions, or is he just reacting too heavily? This also needs to be tested. Those two are test scenarios which you can test in driving simulators, and some of them are already implemented. Now, long-range sensing, things like that happen. Washing machine, or this one was a dryer in California, by the way, which was there on the highway. I moved it out of the way. But yes, if you drive long enough, you see things like that. But this is the more common case. There was an accident and you drive into that. I also have been in a situation like that where it had been rainy, but when I came there, it was still wet, but no more rain. And I was not aware that there was an accident like that, but the police was not already there. So it's tough to go through. But if there's spray, your visibility is reduced. You have to be aware of your sensing horizon. That's the important question for testing. How do you do cooperative long-range detection? And if you know something about the traffic ahead, do you really know it reliably, or is it just an idea? So how do you work with the loss or the quality of your electronic horizon? What is the state of the road ahead? And if you have warnings, shouldn't there be a standard on how do you communicate warnings and what kind of severity there should be there? It's still missing. I want to use the last minutes on 2 points. One is the following situation, and the other one is the signaling. Those following situations, like here, there are unexpected situations, and this is this cutout scenario. And if the vehicle in front of you would crash into it, you still would have a very similar situation, even more severe. And that happens with a lot of other situations, and they are not controllable, and they are not in the regulations for testing. Yeah, that's a visualization of that situation again. You drive in the vehicle under test, this vehicle is not braking, and this crashes into it, and you can simulate what will be able to work. And that one was with 100 kilometers per hour, a distance of 2 seconds, and a maximum deceleration of 8 meters per second square, which you normally don't reach. Then you can just avoid it. You can calculate this, how much distance do you have available with your safety distance and your reaction time. And you can have several combinations, but the effective time gap, those are those lines. They come up with the time you leave and minus the reaction time you have to react. So this is the distance you have for braking, and this is the distance you need for braking, depending on your deceleration. So the 6 meters per second in average is can be achieved quite well. 8 sometimes, and 10, it's more or less the physical limit. And that was the point we have seen before. If you drive with 130 kilometers and you drive with 50% of the speedometer and 0.6 second reaction time, that's the German recommendation, then there's 35 meters missing when you crash into the vehicle. So something like that happens, and so there is a safety gap if such situations occur. And I think that's severe. I don't want to drive in traffic which have vehicles like that. But it's the human drivers which make the fault. But the autonomous vehicles following in a close distance have no chance at all. So there needs to be a solution for high-speed driving. And here is another chart. What is the residual speed when you have a missing distance to a full stop? And okay, I go through that very fast, but there's the severity index of SAE, and also a rule of thumb, which we were using. If you crash up to 30 kilometers per hour residual differential speed, your crash zones will, your crumple zones will handle that. But up to 60 kilometers per hour, there are regulations that the airbag should save you or test cases, but beyond that, no way. And it depends on the way how you brake, how you design your brake. If you design it for very strong braking, then there will be some situation where you don't make it. If you design it for soft braking, then yeah, much less situations which become dangerous. In total, that means there is this pyramid of situations. Normal driving, and you come near collisions, and up there are collisions. There are only a few collisions, but we want to be safer. If you want to decide whether you want to activate your emergency brake, then it's fine to have a binary safety metric, which tells you now it's the last second to brake. Brake, full brake. But what you really need is, for autonomous vehicles, some measure to start with potential conflicts and start to reduce the risk, start to increase your safety distance, and you need something else than a binary safety margin. You need continuous safety margin, or continuous safety or criticality measure, which tells you, oh, no, I'm very, very unsafe down here, or always safe up here, and I'm somewhere in between. And if I come too close to the very unsafe side, I have to do something to come back to the safe side. You can show that in this slide. You have different situations, normal situations, rare situations, extreme situations. They all take a different safety distance to be controlled. And any decision which you make does not work for all, or you have to put it very far here for a long safety distance, but that's not applicable in traffic. You have to put it somewhere here, but you cannot decide. With such a safety measure, with a safety index spread or a criticality index spread, you can say, okay, normally I cover all the normal situations and I cover some of the rare situations. But for merging, like I'd shown before, you can allow to have shorter safety distances temporarily for situations where you really understand the situation, where you have complete knowledge about what happens, and it's very unlikely that something will happen in the next 5 seconds. But then, when it's getting rainy, slippery roads, or you don't see what happens in front of your car, you have to switch to a rare or an extreme mode and go more to the reliably safe side. And this needs, you have to detect your situation and adopt to the conditions which require increased safety levels. The merging is one of those situations, as I said, but I want to point out the safety margins which you need for that is also the language how vehicle or drivers, human drivers, communicate for cooperation. It's the dynamics of safety margins. If you open up a gap, no matter how small or how big it is, that's a signal you can move in. If you close it, you say, no, that's my go behind me, and then naturally the gap behind you opens. So I think there is a field of research. It can be modeled and measured with continuous safety metrics, and there's a list of things which can be done. But I skipped this. Who wants to read that can look at that. I have 10 more minutes. I started a little later.
Yes, we can have 10 more minutes. You also said the one who wants to read that later. I've already been asked if you like to share the slides afterwards.
It's already prepared. The PDF of the slides is available. Looking at using communication. As I said, there are those situations where you would like to know more about the road ahead. The scenarios in Pegasus, they used layers to describe all the situations, but they didn't use the digital information. And it's really not well covered by most of the scenario descriptions. What is the digital information you have about the road ahead? With this accident, if you had known that there was a standing traffic jam, you could have reacted earlier. You would know, okay, this car cannot continue driving as it does in front of me, and I have to slow down because of this electronic horizon which goes beyond the vehicle just in front of me. And some people say, okay, with the radar I can see below the vehicle in front, and I can see the vehicle in front as well. As far as I know, this is working well with moving vehicles, but when you approach a really standing end of a traffic jam, the radar will not be able to recognize whether it's whatever, a pothole or whatever, where the reflection comes from, or if it's really a standing car. I need to say one more thing. All those situations normally have several conditions that they lead to a dangerous accident. And one condition is, of course, the relative speed, or the speed which you are driving and the possible relative speed which you can expect. The second is whether you can detect it with your own senses. And if you really have the full picture, then you might do it. But if you lose this horizon by a vehicle which obstructs your view, or if you have an electronic horizon and this is not reliable, then you better take slower speed and larger distances. There are hazard warning functions of TomTom and also of HERE, which tell, okay, we will be able to communicate actual traffic hazards or actual environmental hazards. They all rely on one single vehicle telling it to others and then telling it to one others. But these are dynamic situations, maybe that not. This here is really not a dynamic situation. It's a quasi-static situation. You can report that. Also, consistency check might be possible, and maybe also telling, oh, there is an object on the road. There are standards down here, data for the road safety, which have defined how to transmit this, but it's not really operative. That needs to be implemented. It's possible. Communication might not be available in the millisecond range, which is necessary for emergency braking, but it is dependable, or it might be dependable within seconds or minutes. And that's fast enough for tactical safety actions, like slow down, increase your safety distance. And I believe the crowdsourcing of traffic hazards is one way of doing that. Maybe not the only way. There are lots of people in the world who can invent other ways, but I want to show how this can be done with crowdsourcing and cooperative sensing. It uses only state-of-the-art sensors, not something which can detect heavy rainfall, icy roads, or something like that, which is not really there. Every car would communicate the speed at which it is driving. This would tell much about the traffic on the road ahead. If there is an accident, the speed will go down, but every car will be able to communicate that. You don't need a sensor to detect there is an accident, but you detect, oh, there is slower speed. And really, it's not the accident which is the danger, it's the slower speed which is the danger for your car. The essential point is the step from reporting hazards. Oh, okay, I tell you what I've seen sometime, but it cannot be relied on. You need a dependable information about the road status with actuality and known completeness, at least for high-speed roads. If you had cooperatively sensing vehicles which provide their speed and, of course, the lane which they are driving on, then you could build up a very reliable network which may function like that. You have sections of the road, you might have speed ranges, and you tell in that part of the road there is the speed range as a maximum, as a minimum speed, maybe also maximum and other speeds, average speed, but you also need to tell how much reports you had in the last 3 minutes. Map providers like TomTom here can do that, and they would be able to do that if they had car suppliers which would say, okay, yes, we do this. We send our speed information to your map building computer. Of course, if you do not only send your own speed, but also the speed of the other vehicles, the other objects around you, which your radar has detected, then you could cover unequipped vehicles, lost objects, pedestrians, animals, even the oncoming vehicle could be detected. And with that, you have those hazard warnings, which are on the roadmap of the map suppliers. It would be supplied within this speed profile. The speed profile is something which you could use right away, which can be used by human drivers as well, or by an assistance system, a level 2 system, advising the driver, oh, for this situation, I would drive a little slower or with a longer safety distance. It can be implemented with the systems which are already in the vehicles. The speed is very easy to detect. It's available, and it will be implemented, or it can be implemented if you have slow driving trucks and fast driving private vehicles, luxury vehicles. You will have a very fast coverage of the complete road. The role of communication is essential for fast driving, but it is not defined yet. What is really the safety role of communication? Only with metadata on completeness and latency, as well with an inverted warning logic. So you don't increase your distance only if you have a warning. No, it has to be inverted. Your default would be a long distance, and if you know definitely there is no danger on the road, then you can get closer. The important thing is you need the prevailing speed of the vehicles on the lane. I propose that something like that should be in the regulations in the EU or worldwide. I'm working as a consultant for the EU, and we have discussed that a lot. It's not making it in this year's regulation for 130 kilometers per hour, and I'm very unhappy about that. But they are thinking of putting something like that in the next regulation term sometime in an update. If you want to test for tactical safety, you of course have the sensing, perception, planning, and control. But the tactical part is you need the awareness of risk, the caution and cooperation and behavior modes. What that needs is looking at internal conditions, vehicle and driver state. At outer conditions, especially the sensing and data quality, how far can you look? What is your sensing horizon? It has to understand, of course, the situation and the prediction, what will others do? And from that, it tells behavior guidelines for the planning. What is the safety distance? What is your speed, your advised speed? It might be much lower than the speed limit. And you have the event data recorder and the safety metrics, one to document what you did for the question of the judge, and the other one, the safety metrics. Why did you come to this solution on, oh, I have to reduce the speed, or maybe even there was no danger for me to see, I could continue with the speed. And all this structure is something which you could test separately and evaluate in a safety audit. But it also needs the safety metrics and the communication outside, which was missing up to now. Maybe with monitoring cameras or any other things which monitor the road, but also the traffic participants which share their knowledge about the road and the whole thing. These two things, the traffic database and the continuous safety metrics, are important features which are not well developed and which need further research. And maybe you can work on these fields, among others, of course. Okay, and when you test it, that's how we work now. How do you test in the regulations? If you have some feedback like that, what the vehicle sees, it's much easier than if you just have this situation. If you let the vehicle drive in that situation and you cannot visualize what the vehicle sees, it's hard for an examiner to give the sign off of the vehicle. So some visualization like that needs to be done in order to tell the examiner that the vehicle recognizes dangers. And of course, here is a vehicle which comes in there, and to show that the situation is understood by the vehicle, even though there were significant occlusions, it's important to tell in a very short testing phase, okay, this vehicle behaves safe enough. Summary: have a clear understanding of quantitative measures and the risk of driving. The continuous safety matrix, I think, make the situation awareness observable, especially if they are also visualized. The second, apply continuous, complete and vigilant monitoring. I think the cooperative sensing plays a significant role, and this has to be extended. And know your available actions, and to reduce the danger, the early and smooth tactical actions help to avoid uncontrollable dangers. So my summary: human drivers take the risk of short safety distance because they assume the highway is usually free of traffic hazards. But AVs should know that the highway is safe when they are designed to drive at even shorter distances. And that's the shorter distances is really the significant clue in improving traffic effectiveness of autonomous vehicles. Without that, it will be less efficient than human-driven drivers. So yes, this knowledge and not assumption of the traffic ahead is one very important aspect. So all those ideas are put together in the Handbook of Driver Assistance Systems, which will come out at the end of the year. Maybe you know the third edition of that. And at this point, I want to say goodbye here. It's not the warning sign, but you all understand this, and that's a human intelligence, and the artificial intelligence can do a lot. I believe in that. But there's still ways to go to be equivalent to the humans. Thank you for your attention.
Thank you very much. I'm sure we have some questions.